Okay, let's start the session 3, effect of pressure on steam formation and properties of steam. So this is under session 3. Again, it is under unit 1, that is formation of steam. So in this session again, we are going to cover the summary of previous session. So previous session, what we have covered in the previous session, again we are going to see that the highlights of the previous session. The next one is external work done during evaporation. So what is the amount of work done during the evaporation? That also we are going to see in this session. And entropy of steam and steam tables and their uses. So these steam tables and their uses are very important. So first we'll start what is the latent heat. So before going to start this latent heat, so what are the topics we had covered in the previous session? So previous session means I told you how the formation of steam takes place under constant pressure. So keeping the pressure constant, how the steam is going to form. So you need to supply the amount of heat to the water, then the water gets converted into a wet steam, dry steam and supersaturated steam. Right? So this variation I have shown it in the diagram with this side, one side is a heat and one side, that is in x-axis is a heat, on y-axis there is a temperature. So that diagram I have shown you. So during the latent heat of evaporation, the temperature remains the same, only the wet steam gets converted to dry steam. So that during the latent heat of vaporization phase, so what is the changes going to take place in the steam conversion? So that part now we are going to study here. So that is the latent heat is utilized for the following two purposes. What do you mean by latent heat means? I have shown you something like this drawing. So this drawing from this point to this point, so what I have called this as sensible heat. From this point to this point, it is latent heat of vaporization. Again from this point to this point, I told this is superheat. So these three phases we have seen in the previous session, right? So this middle portion, so this whatever there is a horizontal line is there, so this portion we called as latent heat, the latent heat of evaporation or vaporization. So during this stage, what is the changes going to take place while forming the steam, right? So first, during this stage, whatever the amount of heat you are supplying to the system, so that heat is utilized to overcome the internal molecular resistance offered by water while changing its state from saturated water to dry saturated steam. So initially from A point, the temperature is 0 degrees Celsius, that is water at point A. When it reaches at point B, so at the point B, it is super means we call it as saturation temperature. It reaches 100 degrees Celsius, means it is a boiling point. So up to this boiling point, there is a whatever the amount of heat you are supplying, that heat is absorbed by the water. Then from the point, this point to this point, there is a conversion of wet steam to dry steam takes place, right? So this is called as internal work or internal energy. I told you in in your previous semester, the internal energy means the amount of heat supplied initially, it is absorbed by the water molecules to gain the hidden energy. So that energy we call as internal energy, or you can say this stored energy in the steam. You can say this stored energy in the steam. Whatever the energy you are stored in the steam, so that is called as internal energy or internal work. Internal work means there is a movement of molecules of water takes place here. So that is called as internal energy. Then second one, to overcome the external resistance offered by the piston during expansion of the steam. Initially, the amount of heat supplied to the water is absorbed by the water molecules, then it gains the energy. So that energy is stored in the steam, that is called as internal energy. And in the piston cylinder arrangement, on the top of the piston you have placed the weight, some amount of weight you have placed. Why you have placed the weight? To maintain the pressure constant. So that weight what you put on the piston, that is considered as external resistance. So that is the force you are putting on the piston, that is the weight you are putting on the piston. So in order to do the work, it has to overcome that weight. So it means the piston has to push upward. So when the piston is moves upward, it means it overcomes the resistance or it overcomes the weight, right? So in these two work, means these two activities takes place during the stage B to C. From B to C, that is latent heat. The latent heat is utilized in these two purposes. This is very important. So now we will see what is the amount of work done during evaporation. So work done during evaporation means during evaporation phase only the piston starts moving upward, right? So I have shown in the cylinder diagram, in the third diagram. So there is some portion of the wet steam was present, and below again there is some amount of water was there, right? So that is the where the evaporation takes place. Then what is the amount of work done? Work done, W is equal to pressure into change in the volume. So this you know, so pressure P into V, that is P into dV. This you have studied in basic thermal engineering, that is work done, right? Work done is pressure into change in the volume. Then P is a pressure, here P is pressure. So P into 10 to power 5 I am writing. Why 10 to power 5? Because P is in bars. So to convert bar into again joule, you have to take into 10 to power 5, right? P in 10 to power 5, then into Vg minus Vf. So this is during evaporation he is saying Vg minus Vf means Vf is, this is the volume of the water, initial volume of the water. How much amount of water you have taken in the cylinder, that volume is Vf. Vg means this is the after expansion, after evaporation the volume increases. From that volume if you subtract the initial volume, so that volume you will get it the evaporation volume. During evaporation the amount of volume you will get it, right? So this is the change in the volume, then you will get change in the volume. Final volume minus initial volume, you will get the change in the volume, right? This is P into dV. dV means change in volume, that is Vg minus Vf. So after this is 100 into P, again Vg minus Vf. So I have not changed anything. Instead of 10 to power 5, I have written here 100. Why I have written 100? Because I have made it, this is kilojoule. Earlier it was a joule, so now it is kilojoule. Kilojoule means out of 10 to power 5, 10 to power 3 comes here, that is kilojoule. So the only 100 remains, so I have written 100 P Vg minus Vf, right? Then next coming to here 100 P Vg kilojoule. So it is as it is 100 P Vg kilojoule. So if condition is given, if Vf is very less than Vg, so initial volume is very less than the final volume, then the initial volume is neglected. When you neglect the initial volume, this Vf becomes 0. If this becomes 0, then it remains as it is, that is Vg. So because of that I have written here Vg only, so leaving the Vf, right? 100 P Vg kilojoule. This is the work done during the evaporation phase. So next one is wet steam. So earlier this is the dry steam, this is work done during the dry steam. If it is wet steam means, when you will say it is a wet steam, when there is some amount of water particles are present with the steam. If there is a water droplets are present with the dry steam, then it is called as wet steam. Then how we are going to define the wet steam? Wet steam is defined with respect to dryness fraction. So dryness fraction is defined the amount of dry steam present in the wet steam to the total amount of wet steam, that is given by X. So the same formula, if you multiply by X, then that gives the wet steam work done during the wet steam. The only change is X here. Why I introduced X here? Because it is a wet steam, then dryness fraction comes into picture, so I introduced the X here. The next is superheated steam. So superheated steam, again it is same. So same formula again, 100p instead of Vg I have taken V soup. V soup means it is final volume. When the steam is superheated, during the superheated steam, so the volume is V soup. Then multiply V soup, then you will get the work done during the superheated steam. So you have to remember, initially there are three stages of steam. So one is initially there is wet steam, dry steam, superheated steam. There are three steams. So for all the three steams, you need to find out enthalpy, then entropy, then specific volume, then you have to find out work done. So for all the three, wet steam, dry steam, superheated steam, right? So this is the work done during superheated steam. So now you have to find out what is the total amount of work done during the steam formation, including from the initial condition. So this is individually we have calculated the amount of work done. Now we need to find out what is the total amount of work done by all the three phases. So when we cross all the three phases, so what is the total amount of work done? So work done while forming superheating steam. Superheating steam means from initial stage, from water to superheating steam. For initially, so it was water, then again it enters the phase of wet steam, then it reaches the dry steam, then it forms the superheated steam. So all, if it passes all the four stages, it means ಎಲ್ಲ ಸ್ಟೇಜ್ ಅನ್ನ ಪಾಸ್ ಆಗಿ ಬರಬೇಕಾದಾಗ ಎಷ್ಟು ಅಮೌಂಟ್ ಆಫ್ ವರ್ಕ್ ಅನ್ನ ಅದು ಮಾಡುತ್ತೆ ಅದನ್ನ ಕಂಡುಹಿಡಿಯಬೇಕು. ಲಾಸ್ಟ್ ಅಲ್ಲಿ ಇನಿಷಿಯಲಿ ಏನ್ ಕಂಡುಹಿಡಿತೀವಿ ನೀವು? ವರ್ಕ್ ಡನ್ ಡ್ಯೂರಿಂಗ್ ದಿ ವೆಟ್ ಸ್ಟೀಮ್ ಇದ್ದಾಗ ಎಷ್ಟು ವರ್ಕ್ ಆಗುತ್ತೆ ಅದನ್ನ, ನೆಕ್ಸ್ಟ್ ಡ್ರೈ ಸ್ಟೀಮ್ ಇದ್ದಾಗ ಏನ್ ವರ್ಕ್ ಆಗಿರುತ್ತೆ, ನೆಕ್ಸ್ಟ್ superheated steam ಆದಾಗ ಎಷ್ಟು ವರ್ಕ್ ಆಗುತ್ತೆ. So that total work if you calculate, then that is work done while forming superheating steam is equal to work done during evaporation plus work done during superheating. So that is given by 100p into Vg. This is work done during evaporation. 100p V soup minus Vg. So this is work done during superheated steam. So that is equal to 100p V soup. This is in kilojoule. So this is the work done, overall work done during the steam formation. Then next you will see what is the internal latent heat. Internal latent heat means the same thing I told here, something like this drawing. So this is the latent heat. What do you mean by internal latent heat? So the heat hidden or heat stored during this process from this point to this point. So whatever the amount of heat stored here, so that we call it as the internal latent heat. So internal latent heat is the fraction of latent heat of vaporization which is utilized to overcome the internal molecular resistance offered by water while changing its phase from liquid to vapor. So whenever it changes the phase from liquid to vapor, so during its change in the phase, what happens? There is some resistance offered by the molecules of the water. So that resistance offered by the molecules of the water, that resistance it has to overcome. So what has to overcome? Whatever the amount of heat you are supplying, that heat has to overcome the resistance offered by the molecules. So how much amount of heat required to overcome that resistance? So that heat we call it as internal latent heat. So next one is internal energy of steam. So these are all you have studied in basic thermal engineering. All the words are repeating here. Only the notations are different. So internal energy of steam we are represented by capital U or small u again. So as you know, according to the basic thermal engineering, then the amount of heat supplied Q is equal to U plus W. U is internal energy, W is work done. Here also the same thing again. So internal energy of the steam, it is the actual heat energy stored in steam above the freezing point of water. Above the freezing point of water. So whatever the amount of heat is stored, freezing point of water. Freezing point means, so this is a drawing, this is a standard drawing, this initial point, this point is called as freezing point. So from this point up to the piston movement ಆಗೋಕ್ಕಿಂತ ಮುಂಚೆ ಏನ್ ಹೀಟ್ ಅನ್ನ ಸ್ಟೋರ್ ಮಾಡಿರುತ್ತೋ ಆ ಹೀಟ್ ಅನ್ನ ನಾವೇನಂತ ಕರಿತೀವಿ, ಇಂಟರ್ನಲ್ ಎನರ್ಜಿ. ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಹಿಡನ್ ಎನರ್ಜಿ ಇನ್ ದ ಸ್ಟೀಮ್. So that is called as the internal energy. So internal energy is given by enthalpy or total heat. So as I said, during your basic thermal engineering, you had studied Q is equal to, so this is U plus W, U plus W. So here I am calculating internal energy. Internal energy means U keeping this side, so bring this W this side, so it becomes Q minus W. Q means enthalpy or total heat. Now I am using the word here enthalpy, but in the basic thermal engineering we used the word the total heat. So because in this chapter the formation of steam we are studying under constant pressure only, keeping the pressure constant we are studying, right? When you are keeping the pressure constant, the total amount of heat supplied to the system is called as enthalpy. So because of that he is using the word enthalpy here, enthalpy, so or total heat. So this minus external work done during evaporation, again it is same, this is Q minus W will give the internal energy. So then how to write this internal energy? As I said again, all this internal energy formula you have to apply for all the three steams again. One is wet steam, dry steam, superheated steam. You need to apply for all the three steams again here. So now in first one we will calculate what is the internal energy of the wet steam. So this is U wet is equal to H means enthalpy of wet steam minus what is the work done during the wet steam. It is already we have calculated in the previous slides, that formula 100 into, this is into means this is X. X is dryness fraction, 100 X PVG, 100 into PVG, right? Or this is given by what is H wet? H wet means enthalpy of wet steam. This we have studied in the I think in the second session. So how to find out the enthalpy of wet steam? Enthalpy of wet steam is given by, this is the enthalpy of sensible heat, enthalpy of water, this is HF, plus this is the enthalpy of wet steam, X HFG. So HFG means it is a dry steam, enthalpy of dry steam. If you multiply this HFG, enthalpy of dry steam, with the dryness fraction, you will get the enthalpy of wet steam. But this HF is initial steam. You need to supply the amount of heat up to the saturation temperature. So whatever the heat is required up to the saturation temperature, that is HF. By default HF will be there. For that HF you need to add the further addition of heat in the evaporation stage, right? So that is H wet itself is HF plus X HFG, and this is same again, minus 100 X PVG. So this is a formula to find out the internal energy of the wet steam. Similarly, the internal energy of the dry steam. So what is the internal energy of the dry steam? Again U dry. So this is equal to H dry means enthalpy of dry steam. Again minus work done is 100 PVG. This is the work done during the dry steam. So what is again the enthalpy of dry steam? Enthalpy of dry steam is addition of again enthalpy of water plus enthalpy of dry steam here. So this is the dry saturated steam. Dry saturated steam. This HFG is enthalpy of dry saturated steam. HF plus HFG, both this addition will give the H dry. So this again subtract this with 100 PVG. This is the work done during the dry saturated steam. Then next third one is internal energy of superheated steam. Superheated steam means, so this is U soup is equal to H soup. This is again the enthalpy of superheated steam. Again work done during the superheated steam, that is minus 100 PV soup, right? So this is equal to Hg plus CPS T soup minus TS. So this is the amount of enthalpy during the superheated steam, and this is Hg is, this is enthalpy of dry saturated steam. This dry saturated steam, if you add up with the superheated steam, it will give the enthalpy of superheated steam. So this is the total amount of heat, or this is the total amount of enthalpy. So if you subtract again the work done, this is 100 PV soup will give the Again, internal energy of the superheated steam. So next one is entropy of steam. This also you studied in basic thermal engineering. What do you mean by entropy? So entropy will give the, so this entropy gets changes whenever there is the change in the temperature. So this DSE change in entropy is given by, is the ratio of a change in heat to the temperature. So it is dQ by T. So where ds is change of entropy, dq is small amount of heat addition, so it is in kilojoule. T is what? This is the average absolute temperature. Again here also for the entropy, again you need to find out entropy for all the three steams again. Entropy of water, then entropy of wet steam, entropy of dry saturated steam, again entropy of superheated steam. For all the three steams you need to find out again once again here. So then this formula also you derived during your previous semesters again. This is a ds is, what is a dq? dq is m cp dt. So m means mass of the fluid or mass of the water, cp is specific heat of the water, into dt means change in temperature. This is a change in the temperature, right? So because when keeping the pressure constant, we are keeping the pressure constant here, so I am taking Cp. So m Cp dt divided by T. T as it is, this T. So this is dq and this is T. So I am substituting dq in the entropy formula. So now m is replaced as 1 because I am considering unit mass, 1 kg of mass. So this is Cp dt as into T divided by T. Again Cp dt by T. So now ds is on this side, this Cp dt by T is on the right hand side. Now you need to integrate this. So how to integrate this? So integrate from 0 to SF. So initially the entropy is 0, then final entropy is SF. So ds Cp integration 273 to Ts. 273 means 0. So I am taking this in the Kelvin. Temperature is taken in Kelvin. If 0 degree Celsius is there here, then if you convert 0 degree into Kelvin, it becomes 273. Right? So then Cp dt by T. So on the left hand side, differentiate it with respect to the entropy. On the right hand side, you differentiate this with respect to the temperature. So now ds will going to become SF. SF means ds integration is S. And substitute upper limit and lower limit. So lower limit is 0. So you substitute only upper limit. So it becomes SF minus 0. So I have not put one more equation here, SF minus 0. Directly I have put here SF. SF means I have substituted only the upper limit because the lower limit is 0 here. So SF is equal to Cp is a constant. Cp as it is, I put Cp constant. And then what is the integration of 1 by T? 1 by T is log of T. Log of T. So if you substitute upper and lower limit, it is log m minus log n. So then it becomes log m by n. So after applying that formula, I am writing this as Cp log Ts by 273. So it is log to the base E. So when you put this log to the base E to the log to the base 10, then you need to multiply this with the 2.3. 2.3 into Cp log to the base E Ts by 273. Then entropy of evaporation. Same here, SFG is equal to HFG by Ts. What do you mean by HFG? HFG is Q again it is Q. So HFG because enthalpy of wet steam, enthalpy of, this is evaporation. During evaporation, this much enthalpy is required, HFG. So right, so this HFG is nothing but Q. Why? Because we are supplying the heat at constant pressure. The heat supplied at constant pressure is called enthalpy. So I am replacing Q by HFG. So SFG means entropy of evaporation is HFG by Ts. This is Ts is saturation temperature. Then the unit of this entropy is kilojoules per kg. Then next entropy of evaporation for wet steam is given by, again wet steam. So wet steam, so this is the dry steam, multiply this with the X. X is dryness fraction. When there is a dryness fraction, when there is water molecules in the steam, then it becomes wet steam. So then multiply with the dryness fraction on both the sides for the above equation. So it becomes X into SFG is equal to again XHFG by TS. The unit remains the same again here. Then entropy of wet steam is S wet is equal to entropy of water plus entropy of wet steam. Initial stage, I said like this. So this initial stage, whatever there, this initial stage is entropy of water, right? From this point to this point, it is entropy of wet steam. This is wet steam. Up to here to here, it remains wet steam. When it reaches this point, so this point, at this point, it is dry saturated steam, right? So now if we add both, so entropy of water and entropy of wet steam, entropy of wet steam anywhere, here, you take anywhere the point, so all the points represents the wet steam. So S wet is equal to, this is entropy, S means entropy, SF plus XSFG. So SF and what is XSFG? We have found out here just now. So this is XSFG, substitute here XHFG by TS. So again the unit is kilojoules per kgK. Then go to entropy of dry steam. So entropy of dry steam is equal to again same entropy of water and entropy of dry steam. So only the X term will not be there here. If you introduce X term, it is wet steam. If there is no X term here, then it is dry steam. Again all the formula remains same. SF plus SFG is equal to SF plus HFG by TS. So again the unit is kilojoules per kgK. So then entropy of superheated steam. Again entropy of superheated steam. This is entropy of dry steam. Entropy of dry steam means, I told, when it reaches the point, this point, this is dry saturated steam at this point. It is dry steam. So after this point, along this line, it is superheated steam. So because of that, S soup is equal to entropy of dry steam. What is the entropy at this point is dry steam, right? That is SG. We call this as SG at this point, SG. And change in entropy during superheating. Superheating means from this point, if keeps on supplying the heat along this line up to this point, it is called as superheating. So whatever the amount of heat is supplying from this point to this point, so this is the superheat is required here. This is called as super degree of superheat. So right. So during this, what is there is a change in entropy. So that we have to write it here. That is S soup is equal to SG plus CPS, this is specific heat of superheated steam. Then it is log T soup by TS. Then what is SG? SG, I'll write it as SG means it is entropy of dry steam. Entropy of dry steam, how we are going to write it? Entropy of dry steam, SF plus HFG by TS. SF is by default, this is entropy of water, it will be present. So then HFG by TS. So including these two, we call this as SG. This is SG plus, so if now 2.3 CPS log 10, now I am replacing log E, log to the base E to the log to the base 10. So when you replace log to the base E to log to the base 10, then you multiply this with the 2.3. So I have multiplied it with 2.3 CPS log to the base 10, then it is the ratio of T soup, this is the temperature at the superheated steam, to the saturation temperature, TS. So this is kilojoules per kgK, right? So you have to remember, so three phases of steams are very important. The first one is the water, wet steam, dry steam, superheated steam. So in all the cases, you need to find out the equations for all the three steams. So whether it may be entropy, enthalpy, specific volume, in all the cases, you need to write the formula for all the four phases of steam, right? The next one is steam tables and their uses. So what are the uses of this steam tables? So just now what I explained, all this enthalpy, entropy, specific volume, superheated properties of the steam. So all these properties are required in the thermodynamic calculations. So what do you mean by thermodynamic calculations? Where you are using the steam as a working fluid in the engines. So not only in the engines, turbines, you go turbines, then you go for nozzles. So then all this, or you can take the boilers. So in all these, you are using the steam as a working fluid. Wherever you are using the steam as a working fluid, so then you need to study the thermodynamic calculations are required. So then how to make these thermodynamic calculations? These thermodynamic calculations, again you need all these properties of the steam. Enthalpy, entropy, these are all properties of the steam. Right? These properties of the steams are required at particular temperature and pressure. That is the saturation temperature and constant pressure. These two are very important. Then this absolute pressure. So I am showing here in the steam table absolute pressure. This is the temperature. Temperature means it is a saturation temperature. So this saturation temperature varies when you varies the pressure. So different pressure you will get the different saturation temperature. So whenever the steam is used as the working fluid in some of the mechanical components, in such cases it is a time consuming process to calculate the properties of the steam. So each and every stage you need to calculate properties of the steam. So then that is a time consuming, it's a cumbersome process. So you need a lot of time to calculate all these properties of the steam. So instead of wasting time in calculation, what they have done is experimentally they have calculated the properties of the steam and they have tabulated in a table. So that table we call it as steam table. So in the steam table, first column is pressure, second column is saturation temperature, then specific enthalpy, that is HF, HFG and HG. See, he has given here, right? The next one is specific entropy, that is SF, SFG and SG, right? Then next specific volume is given VF and VG. So these are all the properties of the steam. So these properties of the steams are very much important and it's necessary in the thermodynamic calculations. So in such cases, so you need to find out all these properties. So it is a time consuming. So to avoid that, so it is practically calculated all the properties of the steam, certain pressure and temperature, and it is tabulated in the table. So that table we call it as steam table. Right? So then what is the use of this steam table? Whenever you need to solve the problem, you directly take down the values from the steam table. HF value directly you can pick here, this value. HG pick from here directly. So instead of calculating using those formulas and wasting time here, so you can further proceed by taking the values from this steam table. So that is the use of this steam tables, right? The next one is enthalpy entropy diagram or Mollier diagram. It is called Mollier diagram. So enthalpy entropy diagram or Mollier diagram. So what do you mean by this diagram? This diagram is a graphical representation of, this is the graphical representation of, once again, steam table. So this is the graphical representation. So earlier slide we have seen there is the steam table, the values, properties of the values are tabulated in the steam table. So but in the graph it is given in the graphical representation. Only that is the difference. Mollier diagram is nothing but it is a graphical representation of the steam table. So here look at in the drawing again here. So there is a line shown, this is the saturation line. This line is called as saturation line, this line. So this is the saturation line. The saturation line means below this line the steam is wet. ಈ ಲೈನ್ ಏನು ತೋರಿಸ್ತಾ ಇದೀವಿ, ಈ ಲೈನ್ ಕಿನ ಕೆಳಗಡೆ ಏನು ವ್ಯಾಲ್ಯೂಸ್ ಬರ್ತಾವೋ this is wet steam. Above this line represents the superheated steam. It is superheated steam, right? So from this also you can find out the values of enthalpy and entropy. So along the x-axis it is drawn, entropy is shown. Along the y-axis enthalpy is shown. So here this Mollier diagram contains there are totally 6 throttling lines. There are 6 throttling lines are shown here. So one is dryness fraction lines. Dryness fraction lines, it is x is equal to, he has given 0.9 here, x is equal to 0.8, 0.8, 0.9. These are called as dryness fraction lines. and constant volume lines. There are some constant volumes lines are also shown here, the constant volume lines. And next is constant pressure lines. See here shown P 50 bar, P 10 bar, then 5 bar, then 1 bar, so 0.1 bar, right? So these are all the constant pressures are shown here. So then next similarly there is isothermal lines, isentropic lines, throttling lines, right? These are the lines are shown in this, but this drawing is shown only 3 lines are shown because all these 3 lines are out of your syllabus. So only 3 lines are important. Those 3 lines are shown in the drawing. So again, this is the graphical representation of the steam table. You can get the values from this graph, or you can get the values from the steam tables while calculating the problem. Then now we will see one problem. It's a very simple problem. It's the problem 1. How to solve this problem by using the steam tables. If anybody is having steam table, just open the steam table and look into the steam table. So problem 1, find the enthalpy of 1 kg of steam at a pressure of 8 bar and a dryness fraction of 0.8. How much heat would be required to raise 2 kg of this steam from water at 20 degrees Celsius, right? So once again read it carefully, what is given in the problem and what he is asking. Find the enthalpy of 1 kg of steam. So the mass is 1 kg, right? At a pressure of 8 bar. Pressure is given as 8 bar. And dryness fraction is 0.8. When he has given the dryness fraction, then definitely the steam is what? It is wet steam. When there is a dryness fraction, it is wet steam. Then how much heat would be required? How much heat you need to supply to this to get the wet steam of this much dryness fraction? Istu dryness fraction ಬರಬೇಕಾದ್ರೆ ನಾವು ಎಷ್ಟು heat ಅನ್ನು ಇದಕ್ಕೆ supply ಮಾಡಬೇಕಾಗುತ್ತೆ? How much heat we need to supply to it? Means now the water is not at 0 degrees Celsius. You have studied during the explanation of formation of steam under constant pressure, the water starts from 0 degrees Celsius. That is called as freezing point. But in this problem, the water is already at 20 degrees Celsius. The water is already at 20 degrees Celsius. When water is already at 20 degrees Celsius, it means that you would have given some amount of heat to it to reach 20 degrees Celsius, right? So from this problem now, write the solution. What is the given data now? He has given P is equal to 8 bar, X is dryness fraction is 0.8, mass M is 2 kg, then water temperature is 20 degrees Celsius, right? So initial temperature of water is 0 degrees Celsius actually, but now it is 20 degrees Celsius he has given because already the water is at 20 degrees Celsius. From steam table corresponding to pressure table 2. If you have steam table open the pressure table 2. If anybody is having the steam table RS Kurmi, so open the table 2. So in the steam table 2, so I'll tell you the page number also in the. So go to the page number 11. If anybody is having the steam table RS Kurmi, so open the page number 11. In page number 11, refer the 8 pressure 8. So move along the horizontal of 8 pressure. So you will find HF value. So HF value as 720.9 in the steam table. Directly write down from the steam table 720.9 kJ per kg. So if you would have not referring the steam table, you would have calculated this 720.9 kilojoules per kg. This is a time consuming. So because of this, experimentally this is calculated and documented in the table. So that is the steam table. Then next move horizontal again, go to the HFG value. HFG value is given as 2046.5 kilojoules per kg, right? Then what is the enthalpy of 1 kg of steam? So whatever the values documented in the steam table, this is calculated with respect to unit mass, with respect to 1 kg of mass, right? So for 1 kg, this 720.9 kilojoules of enthalpy of water is required for the 1 kg of mass. Then find out the enthalpy of 1 kg of steam. So this is HF plus X HFG because it is wet steam. So HF plus X is dryness fraction into HFG. So HF is 720.9 plus this dryness fraction is 0.8 into HFG is 2046.5. Then you will get 2358.1 kilojoule. So this is the amount of heat required for 1 kg of mass. Right? Then next, the heat already exists in 1 kg of steam at 0 degrees Celsius. So what is the amount of heat already exists in 0 degrees Celsius? You know the specific heat of water is 4.2. So this is the initial heat exists in the water, right? So then heat in the water at 20 degrees Celsius. Now you need to find out what is the amount of heat already present in the water which is maintained at 20 degrees Celsius. In the problem it is given the water is at 20 degrees Celsius. So we know that the water at 0 degrees Celsius, the amount of heat already exists in the water is 4.2 kilojoule. So the water is now here at 20 degrees Celsius. So to calculate this, so multiply 4.2 into 20. So you will get it 84 kilojoule. 84 kilojoule is the heat already you have supplied for this. Right? Now the heat required per kg of steam. Per kg, remember per kg. Per kg this is 235.1. 235.1 already we have found it just now. Minus 84. 84, why you are subtracting this 84? Because already the water is at 20 degrees Celsius. You can subtract this. So you will get it 2274.1 kilojoule. This much heat is required to generate the wet steam with dryness fraction of 0.8. But this is for 1 kg. But in the problem, he has given to find out for 2 kg. So multiply this value with 2. So if you multiply with 2, then 2 into 2274.1. So this is equal to 4548.2 kilojoule. This is the total amount of heat supplied to the water which is at 20 degrees Celsius and to get the wet steam of dryness fraction 0.8. So thank you.